All right, so question number 11. Okay, so the key term here is the speedometers are configured to read the speed proportional to the rotational speed of its wheels. Right, so the speedometers are going to read the speed in terms of the rotational speed of the wheels. Okay, so what happens if you get larger wheels? If larger wheels such as those of snow tires are used, will the speedometer reading be high or low or no different? Okay, guys, we spent quite a bit of time discussing this in class. The speedometer only reads the rotational speed. That's it. It reads the rotational speed. And then when you multiply the rotational speed with the radius of the tire, it's going to give you the tangential speed. The tangential speed is the one that you read on the speedometer. All right. So speedometer reading is exactly going to be the same. It's not going to change. Speedometer reading is exactly going to be the same because it's only reading the rotational speed. Except the car is going to be moving faster than what's on the speedometer because the radius of the tires is larger than what it's configured to be. All right. So the rotational speed is not going to change. Because the rotational speed is not changing, the speedometer reading is going to be the same, except because the radius of the tires are larger than what's required, the car is going to be moving faster than what's on the speedometer. We got the tightrope walkers. They use a pole while walking on a tensioned wire. So how does the long stick help? All right, so a stick provides a rotational inertia or moment of inertia. Moment of inertia, rotational inertia is the resistance of that mass to change in rotational motion. It's resistance to change in, it's resistance to rotational acceleration. All right, so the longer the stick is, the more massive it is, the larger the moment of inertia is going to be, more resistance it's going to offer to rotational motion. So it's going to help you balance yourself in that sense. Every time you feel like you're losing your balance, you're going to lean into the stick to balance yourself. Falling chimneys. Okay, when the chimney is extremely tall, it's sometimes breaking the middle. What's the reason for this? All right, guys, all the way up to the point of center of mass. Okay, the center of mass is going to be falling under the influence of gravity. It's a rate of 1g, roughly about 10 meters per second squared. Anything under the center of mass is going to be falling at a rate which is less than 1 single g. Anything over the center of mass will have to fall at a rate larger than the gravitational acceleration, which means that the system needs to be reinforced to pull the top of the chimney at a rate larger than the gravitational acceleration. The chimney is not reinforced sideways properly to pull the entire structure down at a rate larger than the gravitational acceleration. That's the reason why the top usually breaks and the broken top is going to fall at a rate of 1g. I think most of you guys got this right. All right, so which will have a greater final speed rolling down an incline? A hollow cylindrical disc or a solid cylindrical disc? Okay, the solid cylindrical disc is going to be rolling at a greater speed, which means that it's going to end up reaching the bottom sooner. The reason is because the solid cylindrical disc is going to have a smaller moment of inertia. Remember, moment of inertia is the resistance to change in rotational motion. All right, so the smaller the moment of inertia is, the smaller resistance is going to offer to rotational acceleration. That's what it means. So the next thing you need to do now is you need to explain why the solid cylindrical disc has a smaller moment of inertia. So a moment of inertia depends on a number of things. It's going to depend on the total mass of the system, and both of them have the same mass. And the second thing, it depends on how the mass is distributed relative to the rotational axis. In the solid cylindrical disc, the mass is uniformly distributed. All right, so some of the mass is going to be closer, some of the mass is getting further away, but it's got a uniform distribution. In the case of the hollow cylindrical disc, all the mass is going to be distributed at a radial distance away from it. So the bigger the mass, the further away it is from the point of rotation, the bigger the moment of inertia is going to be. In the case of the hollow cylindrical disc, the moment of inertia is going to be much greater because much of the mass is distributed at a radial distance r away from the point of rotation. So it's not how much mass, also how the mass is distributed actually matters. All right, question number 5. All right, so part of the kinetic energy of a moving car is in the rotational motion of its wheels. When the brakes are applied on an icy street, the wheels lock and the car starts to slide. So what becomes of the rotational kinetic energy? Okay, most of you guys end up getting this right, but you got it partially correct. All right, so you just have to kind of explain the assumptions that go into a question like this. All right, so we're talking about the rotational motion, rotational kinetic energy of the wheels. All right, so part of the kinetic energy of a moving car is in the rotational motion of its wheels. All right, so when you apply the brakes hard on an icy street, the wheels will lock and the car will start to slide. So what becomes of the rotational kinetic energy in the car? All right, car's total kinetic energy is a combination of its translational kinetic energy that comes about because of its linear motion. The center of mass of the car is moving forward. And then also it comes from the rotational kinetic energy of the tires. So it's a combination of the translational kinetic energy of the car as well as the tires, as well as the rotational motion of the tires. Okay, so if you make the assumption that this ice is a perfectly slippery ice, when you lock up the brakes, it generates absolutely no frictional force. All right, when you lock up the brakes, it generates absolutely no frictional force. There's displacement, but there's no net force acting on the car. So which means that no energy is being transferred to the car in the form of kinetic energy, which means that before and after you lock up the brakes, the kinetic energy of the system, the car, as well as the tires, will remain constant. All right, so there's no change in the kinetic energy of the car before and after you apply the brakes. If that's the case, when you lock up the brakes, the rotational kinetic energy is going to turn into the translational kinetic energy of the car, which means that the car is going to speed up just a little bit.